Okay, happy Friday, everyone. At today's lecture, Beluga specific lecture, we're going to cover symbolic math in JIT, which is just-in-time compilation. Okay, so if you remember last week, that we had three reasons that indirect methods tend to not be used historically. The first, which is actually the one we're going to be dealing with today, is that deriving analytical expressions for complicated nonlinear dynamics is difficult. And then that's, of course, everything we've been doing on the Wednesday lectures. And then the two other ones, which I'll put in kind of a shorter form here, is the region of convergence for BVPs can be very small. And this is particularly the BVPs that come out of optimal control theory. And then we dealt with that last week. So let me put a little check mark. And then that was continuation methods, right? That's how we get past this small region of conversion. And then the third one, which we will deal with next week and the week after. I'm not 100% sure because the ordering is kind of mixed from what we're covering in the kind of analytical lessons and what we're covering in these coding ones, but is that solving problems with complex features like path constraints is prohibitively challenging. So yeah, in almost every case, like I've spent my entire graduate school career avoiding using the old method to solve problems with path constraints. So that's for the future, but right now we're going to cover this first one. Once again, returning to last week, we have, as a reminder, we have a flow chart of Beluga. And then we start with some input script, which interfaces with Beluga, which defines a kind of like string version of an OCP, like an optimal control problem. And then coming out here, we have our guess, the stuff we dealt with last week, the guess and the continuation sequence. And then we kind of have a three-step process. Let me note that this is defined with string inputs, but it's a little complex, and I'll show you kind of what happens in a great overview. But the user input strings, and then it goes through kind of a symbolic step that uses SymPy. And then so it converts the problem into symbolic math, and then it derives the necessary conditions on that. So then out of that we get a symbolic BVP. So within this, we get a symbolic OCP, which then we convert to a BVP. And then that gets put into JIT compilation. Sorry for switching between different writing styles. But out of this, so we convert that symbolic representation that SymPy uses. We kind of in one step convert it to a Python function, and then we convert it, and then we use just-in-time compilation through Numba that takes the Python function and compiles it to machine code to make it faster. And then this is like comes out as a BVP but defined numerically. And then that goes into a BVP solver. And then to fill in the rest of this from what we had last week, this is a continuation handler. And then there's this out of this comes solutions, and this is outputs. And then this information goes into here, and then guesses and constants go this way. Okay, so like I kind of said already, is what I'm going to be describing today is this section here. The issue with that, so I'm going to be fairly general. One, because there's a lot there, and then two, it's kind of like analyzing a painting before the artist finished painting it. This part of Beluga is, I improved it in others, improved it a lot in the past year or so, but I think there's a lot of more progress to make it clean and efficient. So it might change in the near future. But if you're doing anything in there, and if you're anyone who's going to be in the group of people contributing to Beluga, just talk to me and I'll keep everyone up to date on what's happening, who needs to know or wants to know. Okay. And then one last kind of thing before we go on to coding is that these 3 steps that we take, as I already hinted at, address like kind of, well, they're kind of different than the steps there, but they're the same ones, just spelled differently. So we have issues, and then we have solutions. And the reason why we do the process that we do is we have the first one is that the user doesn't want to do math. Right, so no one wants to go through the optimal control problem, apply calculus of variations, and derive the necessary conditions if they can avoid it. So our solution to that is SymPy, and then that is a computer algebra system. So it does the deriving of necessary conditions for us. The next one is symbolic math is slow, basically. I'm going to put it very here. It's very slow. So then SymPy, we used to do this through templates, and kind of the process used to be less robust and kind of not as integrated well, and used to use templates. But now we use a feature that actually is built into SymPy, but they call it lambdify. And then that turns a symbolic expression into a like normal numeric expression. like normal Python code. And then we have this other problem, is that Python is, yeah, it's a made up board. I mean, all boards are kind of made up. It is like the letter lambda phi, and I'll show examples of it. That's literally what it's called though. Like that's what you call, and it comes from just kind of getting ahead of myself here, but it out of functional programming. In functional calculus, there's a concept known as like lambdas, and it has to do with like the notation uses like a lambda, a Greek lambda, and it has like arrows. If you have any broader interest in computer science and stuff, you'll probably hear functional programming, and the concept of lambdas comes out of functional programming. Even like there's a language Haskell, which is a functional programming language, and its logo is a lambda. So that's this kind of concept comes out of that. And then yeah, I'll touch on that in a little bit. And then a general other problem is that Python's slow. So then that's where we use the JIT compilation. Keep switching. I'm sorry, I keep switching ways I'm writing. And this is done through a package called Numba. Okay, so let me go here and let me open a new file. So first I'm going to actually go through how to use SymPy and kind of a brief overview. And SymPy is important if you're doing any work on the optimal control side of things, of implementing things in Beluga. So if you come up with some new way to change the problem around, you probably want to do that on the SymPy side of things. And then, so anything outside of the continuation method or the BVP solver. Okay, so let's start by, let me make this larger by the way, just so you can see it well. So let's start by importing SymPy. We expect, and I'm going to be defining, they did not spell that correctly, defining symbols. So there's one way to define symbols. Hold on, let me move things on my desk around so I can actually type wrong. Okay, so we can say something like, we could just call the symbol class directly. We do x is equal to SymPy symbol, and then we give it a name, which in this case is x. Or we could bunch them all together. It's like ABC is equal to SymPy symbols. And here, you kind of just copy what's in the outside. You can actually cheat, like in you never really want to do this in practice, except for some really few edge cases. But I can make this x different than this, and also like I can make this y and x, but that would just serve to confuse you. So I suggest not doing that. And yeah, SymPy tells in its documentation not to do that, even though you can. So let's run this quickly. So if I look, x, it's weird. I'm sorry it does that thing where it gets small. But we have x, and it just kind of shows a symbol x. And then we have a is A, and then we can see the type of that. Not that it's that important, but it's a SymPy symbol. We have expressions in SymPy. And then we can say y is equal to I'm just kind of doing a quadratic equation here, plus bx plus c. If we evaluate that again, we can get y, and like we expect, y is what we put in, and these are symbols. We could also define expressions kind of through, and also another kind of goofy name that they came up with is, they call this simplify. So like turning things into symbols. So I'm going to define an x root, since y is a quadratic equation. I'm going to find its root, or define its root, and I can do that by SymPy, and then I call this simplify, which you will mistype it as simplify and vice versa. So we have the solution to the quadratic equation. We just type it in like you expect. And then I'm actually going to do the second root too, just for something like playing around with this a bit later. So if we run that again, you can see that we have that expression, and it kind of did the two steps we did before of defining symbols in the expression all in one step. And then we have substitution. So I'm going to copy and paste this, but I'll talk, so if you're trying to follow along, you can. So yeah, we define this new variable, and then here we substitute x root in for x. So what we would expect is that y subs is equal to 0 because we're putting the root into the equation. But it isn't 0, it's this long expression, because at this point it just really stuck x root 1 wherever x showed up. So it didn't do any kind of simplification. So then to show that it's actually 0, we can do this step. So y should be 0, and then here. So let me just call it down here as well. Yeah. Sorry. Simplify. And it's 0. So once you simplify it, it comes out to be 0. And so the next one is going to be solving. So we could use SymPy to solve equations. And you can imagine if you want to solve for the control law, like the partial of the Hamiltonian with respect to the control should be equal to 0, and you want, what you want is an equation that says my control is this. So you can use SymPy's solve ability to give you what your control options are. So in this case, we just call SymPy.solve on our equation, and then what we're solving it with respect to. This is included because we also have A, B, and C. So if I run this, and then I type it out. See, we get the two solutions. So we know this equation, right, has two solutions, and we get both of them as expected. Another thing that we can do is differentiation. So this is actually what we use SymPy probably the most for, because if you remember, we have all those partial derivatives and the necessary conditions. So that is fairly simple. You can say y prime equal to I, and the method is diff, and then we can do that with respect to x. So let me just type this down here. It's faster, and we get what we expect 2ax plus b. Then that's the derivative we expect. And then now we get to the kind of lambdafied step. And just going to turn, not sure, but turn SymPy expressions into normal functions. This, you can see when I type things out why I copy and paste, because I am a slow typer. But so let's so if I say I want to calculate the roots, the second root of this function y, I can say SymPy dot lambdafy, and then I'm going to say the input arguments are a, b, and c, and the expression is held in x root 2. So if I put that down here and evaluate it, see I get a function out. And then this is callable, and you need to put in a, b, and c. For testing, I'm also going to lambdafy the y function, y SymPy lambdafy, and this takes a, b, c, and then I'm going to put it up here because I did that. X and a, b, and c. So this takes 4 arguments and then each y. And then we can actually test that by, I'm going to define an a, b, and c numerically. So I have num a, num b, num c, and those are just some numbers. And then I'm going to evaluate this x root function and plug it into the y function, and it should be 0. So this should also be 0, like before, like y should be 0. And then we have y function, and then the x is going to be this x root evaluated, and I'm going to put in this a, b, and c as well. So if I run this, and it's lower than machine precision, so it's 0 for all numeric purposes. And I didn't think of this when I was preparing these examples, but this shows like why you would want to use symbolic math and when would you want to use numeric math. So as I'll show in the next file, keeping the symbolic stuff will be slow, but the symbolic stuff, as you saw when we simplified, we did basically the same thing symbolically here, and this y should be 0, and we got exactly 0. But whenever you discretize something and make it numeric, you're going to have numerical errors. In this case, the numerical error is really tiny, but it's there. So that's kind of like one reason to use indirect methods as well, is that the control law is defined analytically, so you don't have numerical errors that show up there. The numerical errors just come after you convert everything, after you do the optimization. Okay, so now I don't think I'm going to type this out because it doesn't, it's not as dramatic as I wanted it to be, but I think it still shows my point. So here I import my number. I'm going to show how the JIT compilation works and kind of speed comparisons. So is that, so if you remember the kind of pendulum problem, like a swinging pendulum, that's what we're going to simulate. So I have this just uses SciPy to integrate the function with constants g, r, and k, which I defined up here. This will plot the function so we can make sure our functions are correct. And then this will do the, I have two versions here. So I can either do the integration 10 times or just evaluate the dynamic function 10,000 times. And then here, so this is how you would, let me make sure all these are commented out. I'll get to them later. Okay, so this is how you would define the function if you were just using Python alone. So let's plot that, make sure it's correct. And it is. So this is a damped pendulum, so it damps out and it oscillates, as we would expect. So let's see how fast. I'm going to do the integration test 10 times. And it took 1.35 seconds. So that's right here. Not that slow, but not as fast. Oosh, sorry. I pressed the wrong button. Oh, there we go. Okay, so that's Python, just pure Python. And then we're going to do, if we use SymPy. So the way I define this is I used, as we did in the last file, simplify, and I'm actually going to simplify an array. And then that's going to have the dynamics, which are theta dot, and then this is the acceleration with the gravity term and the drag term. See how this is the same as up here, but what we get out of it is symbolic. So let me just run that for, so that's running. Close that. And then you can see what this looks like. Right? We have a NumPy array and the symbols in the first one and symbols in the second one. This next thing, I'm going to define it so that SciPy can use it in its integrator. So this is kind of, and she is complaining at, I should zoom in on this. Right? So she is complaining on me and says, do not assign a lambda expression, use a def. I completely agree with that. If you're adding code to Beluga, please do that. But I actually included the line like this to kind of show what where the lambda phi comes from. So Python has this anonymous function wrapper thing called lambda. So you could call it, you could use the keyboard lambda, and then these are the arguments, and then this is what you evaluate. So in this case, we're taking, just like this, we're taking the same arguments, but instead I'm substituting the arguments into a symbolic expression. So I'm using the symbolic dynamics and substituting in what we, where they correspond. If we plot that, we should get the same result. But see, now it's taken a while, right? It's not the best way to go about it. It's taking longer than I expected, actually. Oh, maybe it popped up already. No, I think well, it takes a while. But we get the right results. I tested it before. And then if we do the speed test here, so the last one took a second. this one's going to take like 14 seconds if it stays consistent. Yeah, so it's kind of an eternity. So imagine doing this when you have to solve the optimal control problem like hundreds of times through the continuation. You do not want to use this symbolic math for anything other than symbolic math. Okay, so it's still going. Yeah, it was okay. Well, we're just going to end that now. And actually, that's why I had the second one. It's the one that just does the function 1,000 times. I think this is the one that took 14 seconds. Regardless, it takes a long time, and I won't. Maybe afterwards I'll go through. But so we don't want to be substituting things in all the time. So now we lambdify. So like we had in the last one, we have our arguments in the first column. See how I could put in an array of arguments here. It's smart enough to know what to do with that. And then just the symbolic dynamics. Running that again. And we get the right result. It looks correct. And then if we do the speed test, we get 1.7 seconds. So it's a little bit slower than the pure Python, and that's because there's an unpacking argument that needs to be put in there. So it's a little bit longer than the pure Python, but not by much. And at this point, it is a pure Python function, so we expect the speeds to be nearly the same. Okay, and then I'm going to do these together just to save time, so I could actually show you what the inside of the Beluga code looks like. So we have number JIT and number JIT with the lambdify. So the first one, so I'll explain it here, and then this is, I need to define that as well. Okay, so we have a JIT function. You can use this as a wrapper too, like a decorator is the right word, but I'm just calling it so directly. So njit is what you want to use to precompile, and then if you're using njit, you have to supply arguments because remember Python is slow in part because it's a dynamic language. So the compiled language actually needs to know what each input and output is. And Numba could infer the output, and it could even infer the input when you call it. So like if you call it the first time, it will say, oh, he's calling with floats, so let me make all these arguments floats. But in Beluga, I kind of we pre-specify arguments because we want every runtime to be consistent, and we know we're going to run it anyway, so it doesn't really save us time. So I specify that all these are floats, floating point numbers. Second one's an array of floating point numbers, and then wrap that on the Python function. Trust me that they output the right thing. And then I'm going to do the speed test, and then I do the same thing but with the lambdify function. So we're at 1.3 seconds and 1.7 seconds. Using JIT, we're at 1.2 and 1.3, which is disappointing, and that's why this didn't show exactly what I wanted. So let's rerun the test, and that's because in this case the functions are really simple, and the SciPy is doing a lot of other things that are counting in our timing. So if we just evaluate the functions 10,000 times, you would see a bit more of a difference. So let me include the Python function as well. So we nearly third the speed. So this is, the non-compiled one is 0.03 seconds to do that function 10,000 times, and it's only 0.013, and these are nearly the last two are nearly identical. This also shows that the compilation is doing optimization behind, because if you remember, the lambda-fied function was slower because it has an unpacking step. But when you compile that to machine code, the compiler, which in this case is LOVM, if anyone's curious, that optimizes that and takes out that unpacking step. So an improvement of a third, like a half to a third, is pretty, like 2 to 3 times is pretty good. You actually, with more complicated functions, that improvement goes up even more. Okay, and then, so I have 10 minutes to kind of show you around Beluga now. If there's any questions, let me know as I pull up the Beluga stuff. You don't have to pull up as much as I thought, because I prepared here. So, okay, take the silence to mean that there's no questions. So, you see here I have Beluga open. I call it Beluga master, but this is if you pull Beluga down, this is what you'll see in the file directory. These operations are kind of the process I talked about today, is contained both in symbolic and numeric. What we did last time was in continuation. So first, and this is kind of why it's hard to show, we have, you can ignore differential geometry for now in special functions. What really matters is these 3 files. So let me open them up. So we have the problem object. So if you remember, and actually let me open up an example to look through it as well. So I like this space shuttle target move one. So this object, that when you call Beluga.problem, it's actually importing this class problem. So it's kind of a big object. We have everything you kind of expect in optimal control problems and boundary value problems, and the dualized optimal control problems turning into boundary value problems. So we have independent variables, states, co-states, parameters, co-parameters. Parameters in the Beluga sense are things that are variables that don't have dynamics but still can be changed by the optimization. So we have a lot of other things. I have versions of simplifying lambda-phi that keep a little bit more accounting. And then all these down here, so from independent, these are actually what you're calling when you are doing your initialization script. So if you're curious on what the optimal control problem can take in, it's all these methods. So when we define like time, we call this independent method. Each state we call this. So it's all here, and then we have some other like helper methods and substitution, so you can substitute everything. I really encourage anyone interested in doing Beluga backend or just interested in how the thing works to when you have time to just like look through on this and try to figure it out. It needs documentation too as well. So if anyone has free time, which I'm sure you won't, I can really use help documenting things. But there's also a place too. So if you see here how I have like these structures, so dynamic struct, name dimensional struct, those are put in to kind of make things consistent until we use code. So before we would just keep everything into dictionaries, so I spent a lot of time in particular taking things out of dictionaries and strings and making them symbols as soon as possible, and making it kind of like using object-oriented coding. Not that it, yeah. So all those different structures are stored here. So they basically all have a simplify method and a substitution method. And then you could have symbols with names. So these would be like controls, basically, that you don't specify anything else. You have ones with dimension. Well, actually, that would be control. you get ones with names and dimensions, constants, dynamic ones. So these ones have the EOMs included. Yeah, so these are what you basically load your strings into, and things that can be simplified right away get simplified, and things that can't, basically the dynamics can't be simplified until right before you do everything, because the dynamics will have like constants and other parameters that you haven't yet defined when you define your states. So that's all handled internally. Once again, it's hard to go through this. And then we have mapping functions does a lot, and it's going to be combined relatively soon if I have my way with like kind of another. It's going to be turned into mapping classes. But this is where we actually perform the optimal control theory stuff. So it's kind of, this is in the order that we do it most of the time. So here we apply, so if we define quantities that they are put into the problem there. Momentum shift takes out time and makes it a state that's needed to use SciPy's BVP solver. This EPS-trig does actually the method that Hittich developed called epsilon trig to do control bounding. UTM uses the UTM method, which he also developed to do path constraint bounding, and etc. Rashes is a method to do switches. And dualize does kind of most of the optimal control, virtually all the optimal control. So we adjoin parameters, adjoin co-states, etc. It's hard to go through this now. We have two different control laws. So this algebraic one is what you would expect and classically do, where you set dHdu equal to 0. And like I said before, we use here you can see sympy.solve. It gets used. This differential one is actually my preferred one. It does some more math and gives you a differential form of the control law, which I hope to cover in next week or the week after. Probably the week after. But that way controls like kind of like another state, and you propagate dynamics with it, and that gets away from having to solve an equation, because you don't actually have to analytically solve anything in that case. Yep. Oh, yeah, so I didn't cover this because this is kind of advanced Python. That's type hinting, and you could use it or not. I like using type hinting. So Python, once again, is dynamically typed. So it does that duck typing thing I talked about and everything. But when you're working in an IDE like PyCharm, you kind of want to know what's available. So Python allows type hinting. So Python doesn't treat it any differently, but if I look here, right, I say that this argument is of type problem. So then if I'm typing this out and working on this, like if I go here, right, and I'm like, okay, problem, I can see the methods on problem if I hint the type, because the IDE can see, oh, problem is a type problem. So that's what this colon means. So if you put a colon and then a type, which is just a class behind it, a argument, it tells you what argument it is. And then there's also something which you can see elsewhere that will kind of, you could do, I think it's an arrow. And then if this outputted a problem, then I could do that. And it says that's what it returns. It just is like a helper thing, which I like to use. But thank you for asking. Yeah, so you can go down here in the future and see everything that happens. Hopefully it's kind of clear. But when I have like this compile direct, which isn't used because we can't solve direct problems at the moment. We used to, but now we can't anymore. And then compile indirect. So this is actually what gets called, and you can see the order in which it does stuff. Yeah, yes, of course. So parameters differ by constants. You don't actually give a default value for parameters. So that's what like kind of differs. You could guess. I think it's been a while since I actually used a prop. I don't think any of our examples use parameters, though they should. I've used them, tested it, but the parameter has a guess that you put in, if I remember correctly, but it doesn't have a set value because the parameter is free to change. So if you think back to like parameter optimization, say you want to find like the initial height that maximizes like downrange or something, you could actually set height equal to a parameter and it will change height to satisfy your objective as well. Oh, I'm sorry. Oh, those are keyboard arguments. I'm sorry. I got confused. Yeah, so those are default values. So that kind of goes back to the first Python lesson we had, right? So if I, let me go down here actually and get a Python console open. And I see that we're at time, so if you need to leave, feel free to. But I'm going to kind of talk things through a little bit more for those who can stay. But if we do. Thank you, Eli. I was rushing like crazy. You're right, Eli. Thank you. I got the half hour confused. Okay, now I can take a deep breath. Sorry about that. Okay. I'm like, oh, I did not think that this would take as much time as it did. So say I define this function down here. Let me zoom in. And I have, I don't know, x, and then I have x is equal to 4 in the argument, like that. And then I return x plus 1. So if I call this, I could actually call this 3 ways. So I can say function, and I could say, the kind of normal way to do it is x is equal to, and saying instead of 4, I want to do 2. So it gives me 2 plus 1 and gives me 3. Because if I don't put the x equals, I think it actually just like will put it into the fourth argument, and see it does. It's 2, I can make this 5. So I don't need the equals as long as I'm going in order. But if I don't put anything in here, it's going to give me the 4 and return 4 plus 1, which is 5. And then there's also like, so keyboard, those are called keyboard arguments, and keyboard arguments, yeah, are optional and they have a default value. So that's what all these equals are too. So if you don't specify any of these, the equals is the default argument. But if you specify it, you overwrite the default argument. Does that answer the question? And then I didn't put type hints because you could put type hints for keyboard arguments, but if the type's the same as the default argument, then the type hint doesn't really help. And the type hinting was also like how much I was more or less like carrying that day too. Unfortunately, you know, you have so like some places I have them. See here, I have the default arguments, and here is a default argument for a keyboard because it differs. I have none, but actually, if I'm calling this, is going to be of type local compiler. And on that note, let's go to the local compiler. And this is kind of this is actually might be rewritten in a week because most the steps are going to stay the same, but the way this is handled is going to change slightly. But just to show you kind of where the JIT compilation stuff works. So actually, where do I start? Let's so let me go to mapping, right? So we go through here, and maybe now that I'm not actually running out of time, I could actually talk through this more. So, like I said, and once again, this is kind of a painting that isn't finished being painted, which we're analyzing. So actually, some of these I kind of want options to not do them all. But as of now, you always do all of these. So we apply quantities. So if you specify a quantity, in a problem like the space shuttle target. See, we have these quantities here. When we specify, let me split this here. Get rid of this for now. So these quantities are cycled through. This is short enough where I can actually go to it. And I have a more elegant solution to this. I just haven't implemented it yet as well. So that should be done as yeah. But basically I cycle through or recycle through and substitute these in using just SymPy substitute, which is sub-self is a method on the quantity component structure. So it's also kind of hard to go through this because there's a lot of machinery, which replaced a lot of really confusing machinery. Now there's just confusing machinery, and hopefully this year, with the help of anyone who wants to help, we can put simpler, but still robust kind of mechanisms in place. But yeah, we just substitute the quantities into the quantities and substitute all the quantities into the problem. This step here is to make it so you can put these quantities in any order. So whether you put, density first or drag first or whatever, it doesn't, because they depend on each other. See how rho shows up here? So it's just to make it order agnostic. That's probably too much detail for that, but momentum shift, that makes time a state, stated in a few comments we do have. So it's just coding, but basically what we do is I define a new state and add it to the state list, and then define a new independent variable, substitute that into, define a new independent variable, which I put is the problem's independent variable, and then substitute that in for everything. And then the symmetry stuff that has to do with differential geometry. But most of the problems you're going to be working are not going to have symmetry. They're going to have symmetries, but you're not going to utilize the symmetries or the differential geometry stuff. And I honestly don't know enough to talk about it. Mike Spirapani did research in that area, so he's kind of the expert in all of it. And then this is an important thing to say too. So in the grand scheme of things, and this probably should be included in the flowchart, but it isn't, is that, right, we start with this symbolic problem, which we do the symbolic operations and arrive at a BVP, and then that BVP gets solved. Well, there's the mapping back from the numerical solution of the BVP back to the numerical solution to the optimal control problem we actually wanted to do. And since we do these other steps to kind of simplify that problem, that mapping becomes more complicated. So the way this is currently implemented is the problem has what I call like a solution map chain. And I append a mapper class, and then that will take it. If you feed, let me go here and I can show how this looks. And yeah, so in this case, so you can see the type hinting again. If I feed a solution into this and map that forward, it will add the new independent variable, or the current independent variable is a new state, and then this goes back to differential geometry stuff, and that comes to the state, time having a co-state. Regardless, then we insert the independent state, the new independent, how do I say this? Yeah, we insert the time into the state variable. So we're adding time as a state, and then time actually stays the same because a new independent variable is numerically equal to time at this point, and then I return the solution. And then the inverse mapping does the opposite. So as I go through, and I probably won't go through that many more, for each of these that need it, we have a kind of mapping class that maps numerical solutions. And I hinted before that these mapping functions are going to be changed to mapping classes. On my own private dev branch, I'm combining these mapper classes for numerical mapping with the symbolic mapping as well. So it'll be one class, and then it's kind of more consistent that way, and all the information's in the same place. So that's a short-term goal of mine. So I was hoping to get it done before these lessons, but I just didn't. So epsilon trig does, applies epsilon trig, which we'll cover in the future. UTM applies it. So, like I said, we have all these kind of mapping functions and mapping, like numerical mapping classes. This dualize is probably the most interesting because it does the optimal control theory that we've covered in the Wednesday classes. So, and it uses a join method. So here we join the initial constraints. Here we join the terminal constraints. We start making a Hamiltonian, which in this case is just the path cost. So we start the Hamiltonian by adding the path cost, and then we add the co-states and the states. So if you remember, the Hamiltonian is the path cost plus the co-states and states. We have parameters which can be optimized. The parameters have a co-state too, and then oddly, even though the parameter doesn't have dynamics, this is just a side comment. I find it interesting. Even though the parameter doesn't have dynamics, the co-state for the parameter does have dynamics. So that's where this comes in. And then I've called those co-parameters. And then, other things. So if you use a traditional method, it's kind of what you expect. The co-state EOM is just the partial differential of the Hamiltonian with respect to the states. The diffie-G is the differential geometry stuff. And then we have the additional constraints we add. Algebraic control law, I kind of already talked about that. Differential control law, I'll talk about in the future. This MF is a differential geometry thing. It's like manifold something. It works, but I just really copied code out of that, so I'm not the one to talk about it. And then the squash to BVP, this is where we take the OCP and then kind of combine states and co-states together and combine everything together to get a BVP out, and this is a symbolic BVP. Then we normalize time, so time is so instead of integrating from 0 to final initial time to final time, we integrate everything from 0 to 1, and then that's a requirement of the SciPy BVP solver. And then this analytical Jacobian thing is to speed up computation time. And then, these compile. The directions are basically in these compile indirect and compile direct. This is something I hope to rework in the near future as well. I'm sorry if this is super boring, but I feel like I should at least acquaint where to find things. So the numeric stuff is so that's all the symbolic stuff. It's in the symbolic folder, mostly under data classes. Numeric, that's when we compile things and then do numeric things to it. So if you look, we currently have 2 BVP solvers, a shooting method and a SciPy's BVP solver, which uses collocation. I plan on covering that in the future. Data classes, I think that's actually a simpler thing to go through. Well, actually, so trajectory is the class in which our solutions are stored in, and those are what go through the solution mappers, and then trajectory mappers. I guess I probably should have been more consistent when I made this, but so yeah, this is all the solution trajectory mappers are in this file here. So if you're looking to change something or add something, this is where you go at the moment. If you're looking how to call things, so say you have a bunch of Beluga solutions, you can see kind of what that class looks like here. Numeric problem is the next place. So we had the symbolic problem, and then the problem object covers our optimal control problem. When you first input the strings, and then when you simplify it, so turn it into symbols, and then when you perform all the analytical optimization stuff, that all happens in to the problem class. Then that gets converted to this numeric problem. So all our parameters, and the thing which I'm going to go to now is this local compiler, which is implementation is going to change a little bit, but the concept's the same, and the actual local compiler class is going to stay constant. So there's an issue that arises when you have custom functions or tables, which are that when you do the simplify step or the lambdafy step, you can feed in kind of your own functions in your own, so both symbolically and numerically. So in order to have the capability to take derivatives of custom functions, this is what this local compiler does. And let me go to it. So in it, I have symbolic locals and functional locals. So, and basically what happens is every time we add a symbol, we add it to the list of symbolic locals. Likewise, every time we add a Python function into a problem. So currently that contains custom functions and tables. So we have one example that uses it. It needs to be built out a little bit more. It needs to be built out a little bit more, to be honest, because scaling doesn't work with them yet. So if we go to like a Zamila boat problem, kind of like we did for optimal control lesson, so we have our two states, but this time drift isn't a constant, it's actually this function here, which I defined as drift y. So I add to the optimal control problem this custom function drift y and specify the units, though it doesn't do anything with those yet. I can actually solve this, and that's the only reason that this is possible is through making our own like class. So if we do this, kind of interesting to plot that. Oh, I will come back. Sorry, it didn't plot. It solved it. I know what that bug is. I'll update that this weekend. Regardless, I know I'm kind of meandering through this. I apologize for that. There's no easy way to do this kind of like deep dive, but it should free us up next week when we're going to do this anyway. So basically this local compiler is, where did I go? A non-local compiler is needed to keep track of symbols and functions that are defined. And then inside of that is defined a lambdafy. And that lambdafy is the same lambdafy I showed you in those examples. So we we lambdify things, but we include these modules, and then we compile things. And then this kind of wraps the NJIT function. So, okay. So when I say like JIT compile function, it automatically handles things like making that argument list. And I guess I didn't cover this, the JIT compiler is great because it makes things faster, but it's also a pain because it only could do certain things. So it can't compile every kind of Python thing. So you have to be careful. So there is a backup built into our JIT compilation that if it doesn't compile, and that's what this try except does, if it doesn't compile, it will still run it'll still solve your optimal control problem, but it'll just do it with the lambdafied Python functions. And you want it, it's a slow, relatively. So that's handled here. The same thing with lambdify. So we have a wrapper for lambdify, which is also referenced to the local compiler, and this time it takes in symbolic functions, but these modules, these can be added to, and then that's where you store. Oh, I actually already covered this. I'm sorry. I'm in my own code, and it's and I say my own code because I'm the one who wrote all this section, so I take responsibility for all the kind of crummy things with it as well. But yeah, that's kind of this. And then the numeric problem takes all the information. Where is that? Yeah, when we import things, so we like initialize it based on a problem, and it extracts all the information it needs and stores it, and then it compiles. You can compile it itself. So I have all these compilation steps. And it goes through one and makes sure you have the right arguments. So it compiles the control, compiles the EOM derivative function, and just goes through and does that lambdify thing and then the compilation step all in kind of one thing. And that happens in a numeric problem. And then finally, so once you do that, then the numeric problem will go to the BVP solver, which is stored. So this is like the base argument. And yeah, well, let me do this. I shouldn't have that one. So actually, when this is initialized, it gets initialized with a problem, I think. Now I kind of, yeah, this probably could be represented better. Oh, here it goes. Never mind. Actually, it doesn't get initialized with the problem. What it does is, there's a step that defines all these things and kind of pre-assigns things to the BVP solver. This is another area that should probably be improved, where all you have to do is feed it a numeric problem and some constants, and then it'll solve that BVP, because that's all that's kind of needed. But we add this extra step. Okay, so I know that's probably super confusing. Just look through it, really. Just as long as you don't push anything, which I don't think anyone can at this point, and it can't hoard anything, you can always be pull. So I really suggest, if you're interested at all in the back end stuff, just kind of go through. And the place to start would be this beluga.py, which imports everything. So like you can see what's in the solve method. So if you go to beluga.py and to line 40 with solve, this is what happens one by one. Yeah, so kind of everything I talked through gets called in this when you call solve. And I think that's all I have. If there's any questions, I'm happy to have them. Any curiosity things too. Yeah, it's just, yeah, it is. Yeah, that's Beluga's insides. Oh, in case. Yeah, probably. So I guess I can I kind of tease this space shuttle problem. I'll hopefully the solution is quick, but the thing, and if I had more time, I would have stepped through this. But this problem's actually pretty good because it shows a lot. It doesn't show like parameters, but here, if you want to look at this in the examples, you have 3 dot states. Here you have the quantities implemented. You have 2 controls, not just one. There's all the constants. And I like this way. So what this problem does is it finds the maximum cost range of a space shuttle. But it's easier to, and I think this is a good use of continuation. It's easier to find max downrange. So the way this is defined is phi is downrange, theta is cost range. So we start with this, I can't pronounce it. This angle is 0. And so the initial cost that we're solving for maximizes downrange. So like here's the gas. And so we kind of up into this last step, we do everything that's needed to maximize downrange of the space shuttle. And then this last step, I take that angle from 0 to pi over 2. And then we change that downrange problem to a cross-range problem. And you kind of get a good sweep too. So if you're curious about footprints that the space shuttle can cover, this technique will actually also give you a footprint. So I think, yeah, if you want more problems to look at, I suggest looking at this one in all the examples, but I'm kind of proud of this one. The reason why this old space shuttle is here, and this is a reference to where the problem is, this does the same problem, but it does it by changing heading. And then it also holds a flight path angle constraint using this instead of holding it purely. So this one, it was kind of legacy. I'm not as big of a fan of it, but it's faster, so I didn't really want to take it out because I wanted to keep the faster one in there. And so that took 104 seconds, so under 2 minutes, which I think is fairly good for solving, a few hundred. So what do we have? Yeah, and this is the solution. So, yeah. See, we have cross-range here and downrange. If I plotted the entire continuation, you'll see that this goes straight and then it's pushed out. On that note, I am finished. So I'll stop recording unless anyone has anything last minute. No, actually, well, does anyone have any other questions? Because I'll stop recording before that answer.